Welcome to the Introduction to Meteorology lecture series. My name is Becky Beadling, and I am a postdoctoral research scientist at NOAA's Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey. And today I'm going to be delivering a lecture on climate and climate change. So what we're going to cover today first is what is climate and what do we mean by climate change? What are some regional climate controls? And then what causes Earth's climate to change? So looking at natural sources of climate variability in Earth's history, and then looking at anthropogenic or human-caused climate change that we're experiencing today. We're going to take a look at the evidence of anthropogenic climate change, and then what model projections tell us the climate may be over the next century. And then finally, we're going to take a look at what the Paris Climate Agreement is. When we meet in class, we're going to have an activity that's centered on climate change impacts. So first of all, what is climate? Well, we can think of climate as what we might expect to experience based on the long-term average conditions in a specific region in any given month, season, or year. So the conditions we typically think of when we describe the climate of a particular region to someone are, say, the average temperature or a range of temperatures over a particular time period, the average precipitation a region receives. So for instance, are winters snowy or are they typically dry? The prevailing wind directions a region experiences, or its humidity. So if we were to describe the summers in Florida, for example, we might describe them as being humid, while the summers in Arizona we would describe as being dry. So taking Princeton as an example over here on the left, long-term observations of daily temperatures in December tell us that we should expect daily temperatures around about 34 degrees Fahrenheit over the course of December. And a temperature of 10 degrees Fahrenheit would be considered very cold for this month, while on the other end, a temperature of 75 degrees Fahrenheit during the day would be considered extremely warm. And these cold and extremely warm temperatures have a lower probability of occurring throughout December. So going into each month, based on long-term observations of temperature, we have an idea of what to expect in Princeton. Okay, so climate change then is a change in the long-term average conditions in a specific region or a change in the distribution of events. So for example, if the long-term average temperature in December were to at some point shift from having a mean of 34 degrees Fahrenheit to now having a mean value of 44 degrees Fahrenheit, we would consider this a change in the climate. So for this example, this represents an increase in the average and a shift in the distribution of events. So warm events that were previously rare have now become more common, and there are more warm days and less of these cold days that were considered rare in the previous climate. Now, climate change in a region can also look like a change in the shape of the distribution. So in this case, we're talking about the distribution of temperatures throughout December. So as the top panel shows, we might have a situation where the mean doesn't change, but we experience more hot days and more cold days, but the average stays the same. Or we can have both a shift in the mean and a change in the shape, as shown in the bottom panel. So there are a number of different ways that a region's long-term average conditions might change, and in each one of these cases, we would consider this a deviation away from the previous conditions, or the previous long-term average conditions, and a change in the climate. So the climate system itself is composed of 5 main components: the atmosphere, the hydrosphere, which consists of all liquid on our planet, so this includes rivers, lakes, the ocean, the lithosphere, which is comprised of solid rock, soil, and all the materials of Earth's crust, and then the biosphere, which we are a part of, which is composed of all the living plants and animals, and then the cryosphere, which is all of the ice on our planet. This includes ice sheets, glaciers, permafrost, sea ice, and snow cover. So all of these components interact with one another in very complex ways, leading to the regional and global climate patterns that we experience. So it's important to note that many of these very complex interactions we're just beginning to understand through both observations and the use of climate models. So the next thing I want to cover here is some factors that control climate on a regional scale. So the first one is latitude. So the particular latitude that a region exists at exerts a strong control on the climate that that region experiences. So the further a location is away from the equator, the less incoming shortwave radiation or sunlight that is received at the surface. So this distribution of temperature sets up the major climate zones on our planet. So in the bottom right panel, we can see what these different zones are. So from about 0 to 30 degrees south in each hemisphere, we have our tropical zones. And then from 30 to 60 degrees, we have our temperate zones. And then as we move further towards the pole, from 60 degrees poleward, we have our polar zones. So the altitude of a particular region is also a strong control on climate. So locations at higher altitudes tend to experience colder temperatures and experience more precipitation. So as an example, I'm going to take Mount Lemmon, which is in Tucson, Arizona, which is part of the Santa Catalina Mountains. And if you were to drive from the bottom of this mountain all the way up to the top, which you can do in less than an hour, it would be the equivalent of driving from Mexico to Canada, with all the different climate zones you go through and all the different ecosystems you experience. So at the base of the mountain, which is about 2,000 feet, you're in desert scrubs. So you have cacti here, you have different desert scrubs. The climate is very dry. And as you start to rise in elevation, you go through grasslands. And then we go a little further up and we're into oak woodlands. And we get towards the top, we enter into a pine forest, and all the way at the top is a mixed conifer forest when you're at about 9,000 feet elevation. And what's really cool here is there's actually a ski resort in Tucson, Arizona at the top of this mountain. So you can actually go skiing in the desert, which is pretty amazing. So another factor to consider when describing differences in regional climate is how close a region is to a large body of water. So water has a high heat capacity, meaning it takes more energy or heat to increase its temperature than it does for other substances, such as land or the atmosphere. So land tends to heat up and cool down much more rapidly than water. So large bodies of water next to a region tend to moderate the temperatures on that nearby land. So as an example, in the bottom here, let's compare the average monthly temperatures throughout the year in Eureka, California, which is a coastal community, versus that in the inland city of Omaha, Nebraska. Well, we see over on the left-hand panel here that is in Eureka, California, when we look at the temperature difference between what they experience in their winter versus their summer, it's really not that much different from one another. So the climate is really moderate. But if we look at the distribution of temperatures throughout the year in Omaha, Nebraska, we see that there's these really large swings in temperature, where they have really cold winters and then warm summers. So this difference is a result of the fact that there is a large body of water next to Eureka, California, that is moderating their temperature fluctuations, where that doesn't exist in inland Omaha, Nebraska. So another factor to consider, which impacts regional climate, is the prevailing winds over a particular region. So the prevailing winds determines which types of air masses typically moves over an area. So essentially determines where a region's weather comes from. And this direction of the prevailing winds is mostly determined by latitude. So topography, or mountains, is also another influence on regional climate. So mountains act as physical barriers to atmospheric circulation, and they heavily influence both regional and global climate patterns. And one way they do this is by influencing regional precipitation patterns. So in the bottom here, we see a series of mountains, and regions which exist on the left side of these mountains in this picture receive more precipitation than regions that exist on the right side of the mountains. And this is because on the left side of the mountains, we have regions where air is being pushed up the mountain. So we have the ascension of air, which leads to precipitation. And then by the time that air mass reaches the other side of the mountain, it starts descending, and it doesn't have that moisture in it any longer. So we have regions that are experiencing essentially a rain shadow. So the last regional control I want to go over here is how ocean temperature and currents influence climate on adjacent land masses. So the ocean exchanges heat and moisture with the overlying atmosphere, and ocean currents are transporting heat and moisture around the globe. So we can see here that there are particular regions where we have these red arrows here, which represents a warm current. So that's ocean currents that are transporting water from low latitudes to high latitudes. Where on the other hand, we have these blue arrows here, which represent cold currents. So these are currents that are transporting water from high latitude, which is colder, to low latitudes. So as an example, we can compare the climate in California versus Florida. So California sits next to the California current, which is a cold current, which is transporting water from north to south. And if you were to describe its climate to someone, you would probably describe it as being cool and dry. However, Florida, on the other side of the country, sits right next to a warm current, the Gulf Stream. And you would likely describe this climate in Florida as being hot and humid. Okay, so now we're going to switch gears, and instead of talking about regional climate differences, we're going to be mostly talking about climate at a global scale. So there are many processes that impact climate at a global scale, and they operate at different time scales. So for instance, we have tectonic processes, which operate on very slow time scales, so over the course of millions of years. So some of these processes include the movement of continents over time, the uplift or formation of mountains, and the opening and closing of ocean basins. Then we have Earth orbital changes, which operate a little bit faster, but still slowly, so from about 10,000 years to 100,000 year cycles. And these Earth orbital changes alter the amount of solar radiation received by season and by latitude. These include something which we'll go over called Milankovitch cycles, which are responsible for the glacial and interglacial cycles that our climate has experienced. And then we have changes in the sun. So these can operate on very long time scales, so billions of years, to short time scales, so from 10 to 11 years. And this alters the amount of solar radiation received by the Earth. And then we have human or anthropogenic activities which are operating right now. And this results mainly from increasing amounts of greenhouse gases in the atmosphere from agricultural, industrial, and human activities. Okay, so if we took the global average surface temperature as an indicator of the state of Earth's climate, we see that over the last 68 million years, Earth's climate has experienced large changes. So the y-axis on this plot is the average global surface air temperature difference relative to a 40-year average from 1961 to 1990. So we can see that relative to that long-term average, the global surface temperature on our planet about 50 million years ago was about 14 degrees Celsius warmer. So during this time period, scientists refer to as a hothouse, the atmospheric CO2 concentrations were about 2,000 parts per million compared to today's value of 415 parts per million. And there were no permanent ice sheets present on the planet. So over the last 50 million years, the Earth's climate system has been cooling, transitioning out of this hothouse into a cooler climate. So some of the leading hypotheses to explain this cooling from about 50 million years ago to 35 million years is that it was tectonic processes that drove down atmospheric CO2 concentrations and thus drove down the temperature of the planet. So one of these processes, referred to here as the uplift weathering hypothesis, suggests that large tectonic events over this time period, including the formation of the Tibetan Plateau and Himalayas, caused periods of enhanced chemical weathering of continental crust, which resulted in the removal of carbon dioxide from the atmosphere. Other theories also suggest that plate tectonic events that led to the opening of key gateways in the oceans altered ocean circulation in such a way that allowed for more storage of carbon dioxide in the oceans rather than in the atmosphere. So the cooling of Earth's temperature as a result of these processes allowed for the formation eventually of the Antarctic ice sheet and the Greenland ice sheet, transitioning Earth from a hothouse climate to an icehouse climate characterized by the establishment of permanent ice sheets that we see today. So now if we look at the concentration of atmospheric CO2 over the last about 800,000 years that we get from records of carbon dioxide trapped in air bubbles and ice cores, like the one shown here, we see that atmospheric carbon dioxide concentrations have gone through these periods of high concentrations in which the climate was warm, and then periods of lower carbon dioxide concentrations in which the climate was colder. So these cycles are what we refer to as glacial and interglacial cycles. So glacial cycles are characterized as being cold and having large, expansive continental ice sheets. And interglacial periods are characterized as being relatively warm. So the last glacial period, or the last glacial maximum, or what you'll hear to it referred to more commonly as simply the LGM, occurred between about 23,000 years ago and 19,000 years ago. So this time period was characterized by an extensive continental ice sheet that covered the majority of North America, which you can see up in this figure over here on the right. So these glacial and interglacial cycles are actually explained by changes in Earth's orbital forcing, which alter the amount of incoming solar radiation, particularly at high latitudes, which exerted a strong control on these ice sheets up here. And these cycles are referred to as Milankovitch cycles after the scientists that proposed their existence to explain how ice ages or glacial periods start and end. So I'm just going to briefly go through the three cycles here. So the first Milankovitch cycle, which I'll see if this video will work. The first Milankovitch cycle involves changes in the shape of Earth's orbit, or known as eccentricity. And this cycle operates over a period of 100,000 years. So over this cycle, the orbit changes from a circular path to more of an elliptical path, or more of an oval shape. And this cycle influences the length of Earth's seasons. So the next Milankovitch cycle involves changes in the obliquity, or the tilt of Earth's axes, and operates on a cycle of about 41,000 years. So simply, the greater the axial tilt, the more extreme the seasons, with more solar radiation in the summer when the axis is tilted toward the sun, and less in the winter when it's tilted away. So less tilt periods where there's less axial tilt are associated with periods of glacier and ice sheet growth, or glaciation. And when the axis is tilted more, this is associated with periods of deglaciation, or melting and retreat of those large continental ice sheets. Okay, so the last Milankovitch cycle is changes in Earth's precession, or wobble along its axis. And this operates on a time period of about 26,000 years. So this wobbling behavior makes seasonal contrasts more extreme in one hemisphere and less extreme in the other. Okay, so those are the three cycles that are responsible for the glacial and interglacial periods that we're able to track using paleoclimate data over the last 800,000 years or so. So the next two sources of natural climate variability I want to touch on here operate today, and they operate on much shorter time scales, so we can see them in the more recent climate. So another source of natural climate variations involving the sun that operates on a much shorter cycle is the 11-year solar or sunspot cycle. So over the course of a roughly 11-year cycle, these spots on the sun, called sunspots, start to appear, which leads to an enhancement of solar energy. So eventually the amount of sunspots start to decrease and return back to a minimum at the end of the cycle. So you can basically see that here in this figure on the right. So at the start of the 11-year cycle, we start seeing more and more sunspots till it reaches a maximum, and then the amount of sunspots start to decay. So more sunspots are associated with more solar energy, and less sunspots are associated with less solar energy. And scientists can pretty easily track the amount of sunspots that are on the sun at a given period of time. So we have strong records of this, and we can track the amount of energy coming off the sun during these cycles. And we find that the long and short-term variations in solar activity play only a very, very small role in Earth's climate. Nevertheless, we can see the effect of them. Okay, so the last source of natural variations in Earth's climate that I want to discuss is that of volcanic eruptions. So massive volcanic eruptions impact our climate by essentially blasting large amounts of gas and ash into the second layer of our atmosphere, known as the stratosphere. So this results in accumulation of aerosols, which act to reflect and absorb incoming solar radiation in the stratosphere, which leads to cooling of the lower atmosphere, which is what we experience. So unlike the troposphere, or the atmosphere that we live in, where weather occurs, there's not a strong mechanism for removing these aerosols in the stratosphere. So they can essentially circulate for years around the globe after the volcanic eruption. So one of the most famous volcanic eruptions, and really where we as a community learned a lot about the impacts of volcanoes on climate, is the eruption of Mount Pinatubo in the Philippines in 1991. So this eruption was massive. And when it went off, it injected about 15 million tons of sulfur dioxide into the atmosphere, which led to basically an overload of aerosols in the stratosphere. And this, because of the fact that these mostly act to reflect incoming solar radiation, has actually led to a reduction in global average surface temperature of about 1 degrees Fahrenheit, or 0.6 degrees Celsius. Okay, so from paleoclimate evidence, we're able to see that carbon dioxide levels in Earth's atmosphere have varied over time and at different time scales, and thus the temperature of the planet has also varied with those levels. So over the past 800,000 years, we see from ice core records, as we saw before, that carbon dioxide levels have gone up and down. So over the last 800,000 years, carbon dioxide levels were roughly between 200 to 290 parts per million. And then as we came out of the last glacial maximum, we saw carbon dioxide levels settling out about around 260 to 290 parts per million. And then since about 1700, we've started to see carbon dioxide levels really start accelerating. So from about 1750 to 1850, you can see on this plot here that carbon dioxide levels were originally around about 280 parts per million, and during this time period, they really start to take off. And that's because this is when the Industrial Revolution was happening. So we started as humans pumping greenhouse gases into the atmosphere at very large rates. And if we look from over the time period for which we have direct observations, so these were taken directly from measuring the carbon dioxide concentrations in the Mauna Loa Observatory in Hawaii, starting in the late 1950s, all the way up to present day, we can see that there has been this really acceleration of the amount of carbon that we're pumping into our atmosphere. So we went from about 290 parts per million in the pre-industrial era, and then we hit the Industrial Revolution, and it's really accelerated, and now today we're sitting at about 412. Okay, so we're going to switch gears now, and we're going to talk about what is the consequence of all that carbon dioxide that we're pumping into our atmosphere. So what is anthropogenic or human-caused climate change that we're experiencing right now? So there's three main ways that humans are impacting climate. So first of all, we're injecting aerosols into the lower atmosphere. So aerosols you can think of as basically tiny particles that absorb and scatter incoming solar radiation, and they impact cloud properties too. So some human sources include emissions from factories, autos, trucks, aircrafts, power plants, home furnaces, fireplaces, etc. And we're really pumping a lot of greenhouse gases into the atmosphere. So our greenhouse gas emissions has really accelerated. So greenhouse gases are, as you've gone over in class, are molecules which have the ability to absorb and re-emit infrared radiation, long wave radiation. So these include carbon dioxide, methane, CFCs, nitrous oxide, and ozone in the troposphere. And then humans are also altering land use. So the modification of Earth's surface could potentially be influencing the immediate climate of certain regions. So now we're going to look at what the evidence is of anthropogenic climate change, so what the signs are. So first of all, when we look at the pattern of global average temperature, we see that it has risen significantly since the 1800s, so since the pre-industrial era. So 19 out of the 20th warmest years have occurred since 2001. So 2019, last year, was about 1.15 degrees Celsius, or about 2 degrees Fahrenheit above the pre-industrial average. So I'm going to play a video over here real quick. So this will go from 1950 to 2013, and you can see the regions turn more and more red, which indicates warming. Okay, so our surface temperatures are warming and our atmosphere is warming. Now, when we look at our oceans, we find that, in fact, our oceans are also heating up a lot. So when we look at the energy inventory on our planet, so as we continue to pump carbon dioxide into the atmosphere, and we continue to trap more and more heat on our planet, and we look at where that heat is being stored, we find that greater than 90% of the total heat storage is being taken up and stored in our oceans. So that's represented by these blue regions here in this graph. So really, when we think about global warming, really the majority of that warming is happening in our oceans. So in our oceans, we typically think of this as changes in the total heat content. So what we're looking at here is a change in ocean heat content over the upper 700 meters. So you can see that over the majority of the ocean, we're seeing red areas here. So the total amount of heat in that upper 700 meters is increasing from 1993 to 2019. And we can see that it varies spatially, but overall, we're getting a strong signal of warming in the upper 700 meters of the ocean. So another symptom is we're seeing shrinking ice sheets. So there's two major ice sheets on our planet, the Greenland ice sheet and the Antarctic ice sheet. So we can see here they've been able to measure Greenland mass variation, so how much mass it is losing each year since about 2003, I think is when this starts. And we've seen that over this time period, a reduction in 279 billion metric tons per year. So it's losing a lot of mass. And over here on the left, you can see that the majority of this mass loss is happening right along its margin, so where it meets the ocean. And when we look at Antarctica, we see the same thing. So we see the Antarctic ice sheet has also continuously been losing mass over this time period since we've been able to observe it via satellite. And then we can see again here that the majority of this ice mass loss is right along these margins. And in Antarctica, this is regions where we basically have relatively warm water that's pushed up along the coast that's likely contributing to a lot of this melting that we're seeing here, an acceleration of that melt. So that's another consequence of ocean warming. So another thing we're seeing is the retreat of glaciers. So what you're looking at here on the right is pictures that were taken of these glaciers at different time periods. So in the top picture, this is a glacier located in the Andes Mountains in South America, and this is a picture that was taken in 1978 versus 2004. And you can see that this glacier is really retreating. It's essentially disappearing right before our eyes. And the same thing when you look at this glacier that used to exist in 1909 in Alaska, which is non-existent now, or non-existent in 2004. So the World Glacier Monitoring Service monitors the mass changes in these glaciers every year since about 1950, and you can see clearly here that the glaciers are continuing to lose mass all the way through 2020. Okay, another sign of anthropogenic climate change is when we look at what's happening to Arctic sea ice. So Arctic sea ice has been declining since we've been able to monitor it, which you'll see here in this graph, in this animation. So it has been declining at about a rate of about 13% per decade. So what they're showing here is the annual Arctic sea ice minimum. So essentially the minimum amount of sea ice that exists each summer. So we see from this data, we see that really around the year 2000, it really started to disappear quickly. Okay, and then another sign of anthropogenic climate change is sea level rise. So this is really important because about 40% of the world's population lives near the coast. So global sea level has risen about 8 inches or 20 centimeters over the last century, and this rate is accelerating. So when we think about what contributes to sea level rise, the two main dominant contributors here are ocean thermal expansion, or ocean warming, and meltwater from glaciers and ice sheets. And when we look at sea level rise on a regional scale, we see that local sea level change differs from the global average. So the global average pattern shows us that virtually everywhere, sea level is rising. So we're seeing these red regions here on this map. But when we look locally, we see that the patterns really differ from one another. And this is because there are other factors that can cause deviations in sea level, including ocean circulation, local warming that's happening. Maybe it's warming in one region more than it's warming in another region. Changes in land height. So you can actually have land subsidence or subsidence, for instance, that's changing the height of the land relative to the ocean. Or you can have what's called glacial isostatic rebound, which basically is when you have these large ice sheets that used to exist on a continent or that currently exist on a continent, and as that mass is lost, basically the land starts rising because that pressure is not there anymore. So there's actually part of the US that's experiencing that, because back in the last glacial maximum, as I showed on those maps, there was a massive ice sheet that existed over large parts of North America. And also there can be some contributions from natural climate variability. Okay, and then we also have ocean acidification. So this is what I like to refer to as the other CO2 problem. So not only is CO2 warming our planet, but it's also increasing the acidity of our oceans. So that's because the ocean is taking up roughly a quarter of the carbon dioxide from human activities. So for every 4 carbon dioxide molecules that we emit into the atmosphere, about 1 of those gets taken up and stored in our oceans. And as we see here, when you increase carbon dioxide levels, you increase the amount of carbon dioxide in the ocean, which drives down the pH. So since the 1800s, pH has dropped by about 0.1 pH units, which is actually a 30% increase in acidity. And this is because when CO2 dissolves into seawater, water and carbon dioxide combine to form carbonic acid. This carbonic acid then goes on to dissociate into hydrogen ions and bicarbonate ions. So this increase in this hydrogen ion is actually what is driving or causing the reduction in the pH. And this is important because the reduction in pH has a strong negative impact on calcifying organisms, like corals, for instance. So it's really wreaking havoc on the marine ecosystem. Okay, so there is clearly unequivocal evidence that our climate is changing in response to increased greenhouse gas emissions. So what might this look like into the future? So what might our climate look like over the next century or beyond? So the way that we get that information is to use climate models. So climate models, in essence, are simply a mathematical representation of all the different components of the climate system and how they interact with one another. And we can run experiments on these models, making different assumptions about what emissions pathway we might take into the future, and we can look at how the climate responds to that. So in this case, we're looking at the change in global surface temperature. And the red here is what happens under a high emission scenario. So this assumes we basically continue to burn fossil fuels, kind of full speed ahead into the future, versus a low emission pathway or even a negative emission pathway, which requires the removal of some of that carbon from the atmosphere. So we can see here, depending on which pathway we take, we end up with different increases in the global average surface temperature. So when we look at this spatially, a few things stand out here. So first of all, clearly, more emissions leads to warmer surface air temperature. So on the top, you're looking at the RCP 2.6 scenario, which is our low emission or negative emissions pathway, versus the strongest emission pathway, RCP 8.5. And you can see here that if we emit more carbon into the atmosphere, the planet warms more by the end of the century. Okay, and another thing to notice here is that the land warms more than the ocean. And this is directly related to what we talked in the beginning of this lecture about, which is the fact that the ocean has a really high heat capacity, where the land and the atmosphere does not. So the land and the atmosphere warms up much more rapidly than the ocean does. And another thing to notice is that the Arctic regions actually warm more than the rest of the globe. So this phenomena is referred to as Arctic amplification, and it's due to feedbacks involving changes in sea ice, snow, and the atmospheric transport of heat up to these polar regions. So now if we look at what's happening in our oceans in different scenarios, so again, low emissions on the left versus high emission scenario on the right, we see that the oceans are warming. So you're looking at basically if you were to take the oceans and kind of average them together across all longitudes, these are what it would look like. So we're looking at depth versus latitude. So Antarctica is over here on the lower left, and then the Arctic region is over here on the right. And we can see that all depths in the ocean are really projected to warm. Whoops. And that most of this warming is occurring in the upper 1,000 meters. All right, so if we look at the percent change in precipitation under our high emission scenario, so middle of the century by end of the century, a few things pop out here. So first of all, the changes in precipitation patterns are not uniform throughout the globe. So we see increased precipitation at the polar latitude. So again, mostly up in the Arctic region. And we see large increases in precipitation in the tropics. So blue here, blue to green means increased precipitation, while the yellow to brown colors mean drying. So we're seeing also large decreases in precipitation in our subtropical regions here. So this suggests increased drying and possible expansion of desert regions in the future. Okay, and if we look at how Arctic and Antarctic sea ice is projected to change, we see a few things here. So first of all, both regions, both the Arctic and the Antarctic, are projected to continue to lose sea ice as we go into the 21st century. But the largest reductions are really happening in the Arctic versus the Antarctic. So the Arctic is projected to be ice-free under RCP 8.5, so under a high emission scenario by the end of the 21st century. So these are some really big changes that would have really strong consequences for the climate system as a whole. Okay, and then if we look at sea level rise, so as I mentioned before, sea level rise is really a big threat to the world at large because about 40% of the world's population lives near the coast. So they're going to be directly impacted by these changes. So we see increased sea levels. So this at the end of the 21st century. So this line here, this red, is that high emission scenario versus a mid-range emission scenario. So we see that kind of the worst case scenario puts us at greater than 1 meter sea level rise or greater than 3 feet of additional sea level by the end of the 21st century. So this would result in the complete loss of certain coastal communities. It would put us at increased risk of high tide flooding, increased storm surge. So higher sea levels can push more water inland during hurricane storm surges. So this would make hurricane season a lot more dangerous. And then all of this would lead to huge economic consequences. So I've decided in the interest of time to shift our discussion on the Paris Climate Agreement to the in-class portion of the class. So just to wrap up here, so the big picture basically is that the Earth's climate is highly complex and influenced by a large number of factors acting on different time scales. So the climate, as we've seen, has experienced large changes in Earth's history, driven in large part by tectonics and then orbital forcing. There is unequivocal evidence that increased greenhouse gas emissions from human activity has and is drastically and rapidly altering Earth's climate. And model projections suggest large changes by the end of the century if we don't take actions to curb our carbon emissions now. And we'll see this in the in-class portion, but the Paris Climate Agreement provides a path forward for reduction in carbon emissions over the next several decades through the commitment and cooperation of countries around the globe. So I'll leave these next 2 slides for you to read on your own, but these are basically the take-home messages. So what are the main points you should focus on when you're reviewing these slides?